Hello, everyone. I'm Dr. Tina Burns. Welcome back to CS211 for the summer session of Computer Architecture 2025. So today's lecture is 2C. That is the third lecture in the second week of our class. And what we're going to be discussing today is floating point and what that kind of means is in terms of programming. And also we're going to go over the IEEE floating point number and their representations, right? Why do we use them? What is their benefit? And how can a computer represent a floating point value? So floating points, we use them, of course, because they have more precision than our standard integer values, right? Um, and they also are more accurate, right? Saying something is 2.5 will give you a little bit more detail than saying it's 2 or it's 3. And because these are decimal points, right? These are decimal numbers. Previously, there wasn't a standard way to represent them in binary. Now, keep in mind, binary is going to be in the forms of zeros and ones, right? So engineers got together and they wanted to find a way to standardize the representations of these so that you can implement them easily into computers. So that's where this IEEE 754 floating point representation comes into play. So we're going to go through that and just kind of get the basics of it down packed. So the first thing we know, as you know, when you're dealing with numbers in general, is that floating point, of course, is going to be a math standard. We're going to need that when we're doing calculations. We're going to need that, even in simple things. Okay, how much money am I getting back from this? How much interest is growing, etc. And for the IEEE 754 format, all this is doing, as I stated before, is giving you a binary representation of this floating point number. And because you're putting it in binary, now I can interpret it by a computer. Keep in mind that our processors understand ones and zeros only. They're not going to say, 0.5 or 3.07, right? They're going to understand zeros and ones. So if you create this standard, then you can easily represent it in a computer and you can go back and forth between different floating point values. So when we look at how we can apply that, of course, we can use it in numerical computing. We can use it in scientific computations. We can use it in when rendering graphics, right? That's a really, really good example. If we want to change the hue of an object or the RGB scale, which you'll see in a lot of even in these AI generated maps for the intensity of something or where how full something is in an area, right? You can use kind of this numerical format to either increase or decrease your intensity for your RGB scale as you're generating these images. You also can use this as a great, to implement in machine learning algorithms and other areas like that. So as we go through this floating point representation, what you'll need to understand is that there are three components to a IEEE 754 floating point number. The first point is the sign bit. That's really simple, 0 or 1, right? 0 is going to be indicate a positive value, and 1 is going to indicate a negative value. There's going to be the exponent, which represents the scale of the number. And what does that mean? That means you could think of that kind of like the whole number. How large is your number, right? How much space do I have? Is it gonna be 1,000? Am I able to put 1,032 as my number in there? Or is it gonna be smaller, like 8, right? This is what your exponent is gonna represent. And then we have the mantissa, also known as the significand. This represents the precision of bits of the number. What does that mean? How precise is my decimal point value? So if you wanted to look at it in terms of like a whole number and then maybe the decimal point portion, you can say, okay, when we look at the mantissa, the larger the mantissa, the more decimal places of accuracy you're going to have as you're looking at this particular number. So let's go ahead and break this down and really look at how this looks. As I stated, your sign bit is only gonna be 1 bit. Okay, so first of all, let me take a step back. So the IEEE standard, there are gonna be a different number of bits that can represent your number, depending on if you want to represent larger numbers or smaller ones. One of them, one of the most common ones, is going to be a 32-bit representation, meaning I have 32 bits that are used to represent this number. For your sign bit, it doesn't matter if you have 32 bits, 16 bits, 64 bits. Your sign bit is always going to be 1 bit in length. It's only going to be a 0 or 1. You don't need any more bits. Your exponent and your mantissa will vary based on the size or the number of bits you have to represent that number. All right, so your sign bit, 1 bit. For a 32-bit representation, 8 bits are going to be used to represent the exponent. Keep in mind, as I stated before, your exponent is going to be your whole number of the value, right? Or the scale of your number, right? Now, this is going to be before the decimal point. It can be positive or negative, large or small number, and it's going to be biased. What does that mean? Uh, it's going to be biased in that depending on the scale or the size of it, that's going to determine how you represent that. And we'll see kind of more details on that as we go and do some of the calculations that are coming up. And last but not least, as you could have probably guessed, if I have 9 bits already used up, the remaining bits, excuse me, are going to be your mantissa. And your mantissa is going to be whatever comes after the decimal point, and it's more like the fractional value of your number. All right, so 1, 8, and 23, that's going to be for your 32-bit representation. All right, so now let's go ahead and get into some really some calculations on this. You guys will want to pay attention to this because this will be on the exam. So keep that in mind. All right. So first one is extremely super easy. I can easily tell you what my first value is going to be for this first bit. Because it's a negative number, this value is going to be 1. Our sign bit is going to be 1. It's negative. Okay, so I mapped this out to kind of so we can see what each of these represent, right? 1, 8, and 23 bits. Because this is negative, this is going to be 1. Now we're going to look at this yellow portion, which is our exponent bits. Now for your exponent, it's actually going to be multiple steps that you have to perform. It's not just a single step. It's a few things you got to do. There's a few things you got to do here. All right. The first thing you got to do is convert the whole number to binary, right? And we know how to do that. So our number is 53. And one method you can use to convert this is you can take your number and basically divide it by 2. So I'm going to do this. I'm going to kind of write it out here. I hope we don't want this to be white. Let's make this blue. All right, let's say we have 53 here. This is going to be what happens when you divide it. And then I want to have my remainder on the other side. All right. You divide it by 2, and then you get your remainder out. All right. So the 2 divided by this is going to give us 20, 20, 13, 26 with a remainder of 1. I'm going to put my remainder here. When I divide this, I have 13. My remainder here is going to be 0. When I divide this, well, yeah, that's fine. I'll do it that way. Um, when I divide this, my remainder for this portion is going to be 1. The number is going to be 6. When I divide this, my remainder is going to be 0. My number down here is going to be 3. When I divide this, my number is going to be 1, and the remainder is going to be 1. All right? So this is one way we can do it. You see kind of how we did that number and the place it kind of took as we divided by 2, right? This is one way we can get our binary representation. All right. Now, how do we get this to binary? What you do is you start from the bottom. The bottom up goes from left to right. So 1, 1, 0, 1, 0, 1 is our binary representation. And what does that mean? If we go from here to from here, right, it's going to be basically 1 plus 2 so this is 2 to the 0, 2 to the 1. So if I go here, let's do it this way. 1, 2, 4, 8, 16, 32. Right? So we'll have 32. We don't need this, and we don't need this. So 32 plus 16, of course, is going to give us 48. 48 plus 4 gives us 52, and then our 1, that gives us 53. So we've seen that by doing this divide by 2 method, you in fact do get your binary representation of 53. All right, so oops, sorry. All right, boom. Got a binary representation for 53. Another way to look at it is if you wanted to look at it kind of in this graph, essentially the same thing, right? This was I did this as a pictorial representation, but a little bit of overkill, but there we go. We have our number. So now we have our binary number. Now we're going to convert. We're going to do what's called converting the fractional portion to binary. Now, this involves a couple things. The first thing we're going to do is we're going to take this and we're going to multiply this number by 2 until we get 0 in front of the number, right? So if I took this, right, and I did a similar table or similar chart to what I had before, where I have this is my times 2 representation, right? I start off with a number. I'm going to have 0.125, 0.250. Actually, let's not do it this way. Let's do it this way. We're going to put the times 2 over here. All right. We're going to bring this over to this side. And the reason we do this is so that we can see what the numbers are when we're getting back to this, all right? 250, this of course is going to be 0.5. 0.5 over here. Then we get 1.0 over here. And actually, we don't even need this one. We can stop right there. You basically run this until you get a value of 1 at the end, or until you run out of spaces you run out of space on your mantissa representation, right? So let's say you have um we have 23 bits to represent the mantissa, right? So if you get to this and you find that it's repeating and you get to like, 40 different spaces and it's repeating, then you already know you don't need to continue because it's repeating and I don't need the other numbers. So you either get to one or you get to a point where this repeats. And we'll do an example for that. All right, all that to say, my binary representation of this is 0, 0, 1, right? 0, 0, 1. And that comes from these numbers right here that I get from dividing this value. So what is the number right here when I divide this number? That is what's giving our binary portion for this. Okay, so this is our binary representation of that. Now, the next step we're going to do is let's go ahead and combine these two. Remember, our binary representation of 53 was this. We did that earlier. And then here's our binary representation of the decimal portion or the decimal value of that number. All right, so we're already on a great, phenomenal start. Now, we want to take that. So remember I said that this number is biased. What does that mean? It means that there's going to be something that allows us to move this decimal point back and forth, just like your scientific notation is biased, right? We already know, centimeters or millimeters, they're going to have a base number that is going to be dependent upon, and that's how it's represented. It's the same thing or the same theory here when we're representing our numbers in binary. So what we want to do is we want to move this decimal point all the way until we get it to the left, to the right of the first one, right? So our intent is to move this decimal point all the way until one is the first number to the left of the unit, or until that is right, basically to the right of the first one. However you want to look at it. Essentially, we're going to move it from here to here. So that's 1, 2, 3, 4, 5 spaces, right? So this is how we move that decimal point. 1, 2, 3, 4, 5 spaces, right? And because we have moved this 5 places, now we have what is called our bias value. Now, remember I said, just like if we have scientific notation, right? Milli is going to be 10 to the -3, micro 10 to the -6, and so on. For this one, your base value, it's a binary number, right? These are ones and zeros. So your base value or what you're using for this is going to be 2. So I moved this 5 decimal places to the left. So that means if I want to get it back in the original format, I would have to move it 5 decimal places to the right. And this is why we're going to multiply this by 2 to the power of 5. This is our bias here, 2 to the power of 5, right? This is how we're moving that in order to get this to a portion where we can get all the data there, right? All right, so now that we have that, we're going to do something called the precision exponent. So, as I was saying previously, your mantissa represents the fractional portion of the number. When you have your mantissa, it's so large that you're also going to include in there what's represented in the bias. So you have to include kind of the precision of both that the large number overall and also whatever bias you're using in that value. It's going to tell you the number of bits used for the exponent. And this value will always be non-negative. So the precision exponent for this particular, for the mantissa, is always going to be non-negative. It's going to tell you what the bias is, and it helps you really to know how many bits you're using for the exponent. So just to step back a little bit, there are two with your mantissa, and you'll see this as we're doing the calculations. There's two values that you use for this mantissa, this precision exponent, and then also the fractional exponent. You will see this in probably the next slide. Your fractional exponent is going to represent the scale of it. How big is it? And it's always going to be the power of 2 of the whole number. Now, this particular one, your fractional value can be negative or it can be 0. And why can it be 0? Because, I'm sorry, why can it be negative? Because depending on the number, it could be that I had to move this decimal place back a few spaces, right? So it could be a very small number or a large number. If it is less than 1, right? If that value is going to be less than 1, then it ends up being negative because you have to move your decimal point to the left instead of the right. So remember before we had a value where basically we were moving the numbers all the way over. If we were to move that number in the opposite direction, that means it's less than 1. And that's how you kind of get this negative value for your fractional exponent. All right, so we have this value here that we converted in a few slides ago. Let's determine the precision exponent. Again, the precision exponent is predominantly dealing with the bias of the number. How many bits am I using it for the exponent? And it's always non-negative. Okay. The first thing we have to do is this is always going to be your equation to calculate the precision exponent. It will be, that is really big. I want a smaller value. It will be 2 to the n minus 1 minus 1. What does that mean and why are we using that? So we already said for our bias value for the whole number, right, which is going to be your exponent, we have 8 bits to represent this number. That means if I have 8 bits to represent a number and it's binary, I can only go 2 to the 8 minus 1 to represent the number. Like I can't, for example, if I had 2 bits to represent a number, the largest value my number could be is 3, right? It's 2 to the 2 minus 1. And this is essentially telling us the same thing. Because I have 8 bits here, my largest value that I can have for my exponent is 127. If I have a value that's larger than 127, I cannot realistically represent this with the bits allotted for the exponent. All right, so my precision exponent then is 127 anytime I'm dealing with a 32-bit representation for the IEEE 754 standard. 8 bits, that means my largest number is going to be 127. The next thing we're going to do is now we're going to get into the bias. The bias is going to be dependent on how many times we move that decimal place for the value up here. So we have our bias is going to be your precision exponent plus your fractional exponent. Our fractional exponent was right here, this 5 value. Because I had to move this over 5 spaces to the right, to the left, I'm going to add that to this value here. So that's where I get this, this 5. All right. So now I have 5. Now I'm going to take that. So again, this is our precision. This is our fractional exponent. What am I using for that fractional exponent in order to get my bias? Add these two together, I get 132. The next thing I got to do is take this 132 and convert it back to binary. I know this is a little bit of a convoluted way to do the calculations, but it works, and the standard has been working for a while for these representations for these numbers. All right, We're gonna use our same value. What was it? 132. I'm gonna do this one more time just so we can kind of get uh stay familiar with how we're doing our calculations here. Right. 132. I have no remainder here. 66. I have no remainder here. 33. I have a remainder of 1 here. 1, 6. I have a remainder of 0 here. 8, 4, 2, and 1. All right. You always do your division until you get down to 1. So this is going to be remainder of 0, 0, 0, 1, right? So then our representation for this value is going to be 1, 0, 0, 0. Seems a little bit large. Maybe not. Let me see. 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4. 1, 2, 3, 4, 1, 0, 0 is going to be our number, right? So this is our binary representation. Let's go ahead and I'm going to delete this portion. Let's make sure that we got the same value here in my solution, and we should have that. And look at that. That looks exactly like what we were expecting. 128 plus 4, essentially. All right. So there we go for that representation. Okay, so what does that tell us? All of this is for our exponent number. And let me just go back because I see something that I do want to address when we were talking about these calculations here and how we're doing this representation. This is all for your exponent portion of your number. All right, so just gonna present this guy. All right, so now we have all of this for our exponent value here based on the calculations we did here. Now let's go ahead and get the mantissa portion. The mantissa portion is going to be what we already calculated previously from that from our decimal and moving all that over. So we already have our mantissa, and that's just going to be this value here. When you're dealing with this, if you end up having more space than you do numbers, you fill the remainder of it, or you pad the remainder of those with zeros, right? That makes sense. Here's the number that we calculated. Everything else is just going to be 0. And then that's the end of it, right? This is how we get our exponent. And then this is how we get the mantissa. All right, so again, just a reminder of the from the previous slides. When we look at all that we did for the fractional and all of that is going to be based on the exponent calculation. Okay. So let's look at another example because repetition helps us to become better. All right. We already know this one. Sign bit's going to be 0. This is a positive number. Your exponent is 8 bits. Your mantis is 20 is oh, I never finished that. Okay. Well, let's look at this number here. When we look at this, if we wanted to do a different value for a 16-bit representation, it would be the same principle. What you guys can do, I'm sorry, as we're looking at this, you guys can actually do this on your own, and go ahead and submit that in terms of doing the calculations for this. It should be relatively simple. Feel free to do that in your own time. 16-bit representation, which is called half precision. For this, it's still going to be one sign bit. Your exponent now is going to be 5 bits or 5 bits to represent that, and then your mantissa is going to be 10 bits. But it's the exact same process we just followed, just with less numbers. And we already know this sign bit is going to be 1 because the value of the whole number is negative. Now, we're going to convert our whole number to binary. We kind of have an idea of what that's going to be, right? If I start from here, 28, 14, 7, and 3, here's going to be our representation of that number in binary, right? 11100. Now we're going to convert the fractional portion to binary. Now, this is what I was talking about before. Let's kind of walk through this a little bit. This is our ×2 column. We'll have 2 here. We're going to bring this over. We have 4 here. We're going to bring this over. We have 8 here. We're going to bring this over. We have 1.6 here. Oh, I'm sorry. Nope. All right, so we now have brought this 1.8 over. And let's go ahead and bring some lines there. I'm gonna try to be a little bit more organized with that. All right, 0.8. Now, normally this would be 1.6, right? That would be the value. But I don't necessarily care about this 1 once I bring it back onto this side. So yes, it's 1.6 here, but when I bring it back to this left side, I don't want to have this whole number here. So I'm going to truncate, I'm going to take off that 1 in order to provide better, to do the rest of this calculation. So this is 1.6 here, but I don't need it on this side. All right, so 0.6, then this becomes 1.2. Right? Again, all I need is the fractional portion of this. Then this becomes 0.4. And we can stop here. You know why? Because now the number is going to repeat. Remember I was saying you either stop, you stop this when you get a perfect 1 or when you find that your number is going to repeat. And if we look right here, we see that this is the same value as this. So this is where this repeats. So let's go ahead and write that out so we can kind of see how that looks. Portion. All right, so then that means that our number is going to be 0, 0, 0, 0, 1, 1. Okay. And it starts repeating here. So this is right where it repeats. This value here, right? So then I have 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. That's basically what it's going to look like because this is your number that keeps on repeating. All right, so now we have our now we have the fractional representation. Oh, and let me get rid of this. Let me clear my drawing here. Ah, all right. So let's there we go. All right, so now you'll see kind of where you get this number. Everything repeats, represented. This is what you're going to get when you have it in binary. All right, so we take 21. We take our number 28 that we had before. We combine this with this. This is pretty easy to see that we are moving this decimal place by 1, 2, 3, 4 spaces again. 1, 2, 3, 4. So this is now this value is going to be 1.11000000110011 times 2 to the fourth power times 2 to the fourth. Now, the other thing we didn't talk about is rounding. All right. So, like we were saying before, this number goes on and on and on and on. uh, all right. So, because this number continues, just like we do in with our regular fractional numbers, we have to do something called rounding, right? What happens? How do we make a decision what to do with that last bit when we, that goes beyond our previous number? So this is what we do for rounding that unit. If we look at this in terms of scientific notation, keep in mind that I said that there are a certain number of bits to represent the mantissa for this. When we are dealing with a 16-bit value, we have 1 bit for the sign, 5 bits for the exponent, which means we're going to have 10 bits for the mantissa. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This number in red represents the last bit place for our mantissa because we have just 10 bits. So this will be the number that determines what we're going to do for this. This number in yellow here is the number, the bit that's right after it. This will help us determine what to do with this, right? Do we flip it? Do we increase this to 1 or does it stay where it is? So this 0 is your least significant bit. And again, that's the least significant bit because we have 10 bits to represent this value. The post-significant bit is the one that will help you determine whether you should flip the least significant bit. And in this case, we don't need to because, hey, it's already at a value of, it's already, because the bit is 0, we don't need to flip it. If this bit was 1, what would happen is we would flip this to 1 as our point of rounding. All right, now let's go back to, we're going to continue with this exponent. Let's determine our precision exponent. It's the same process, right? We have our 2 to the n minus 1, which is going to be 2 to the 4. I'm sorry, 2 to the 5 minus 1 or 2 to the 4. And then you subtract 1 from that. So the largest number we can get for a 5-bit representation is 15. The largest number for a 5-bit representation is 15. Now we want to do our precision exponent. So it's going to be 15 plus the number of spaces we move, which is 4. That's going to give you 19, right? Very simple. This is what our bias is. and that's going to be the bias for this. Now we're going to take this and we're going to go ahead and convert that to binary. You guys already know how to do this. We've already gone over a couple examples, so you're pretty familiar with that. This is the number in binary, 10011. And now we put that all together. So our exponent here is 10011. Our sign bit we already know is 1 because the number is negative. The mantissa is what we had in our previous example, which ends up being the 110000110. That is our mantissa, and that is the 8-bit representation of our number. I'm sorry, the 16-bit representation of our number. The process, it's a little bit tedious, but once you do it once, or maybe probably a lot more than once, once you do it enough times, it'll understand. It's just a bunch of steps, but you can do this to kind of represent it. So let's do one more example. Let's go ahead and do this 8-bit conversion, and then that'll wrap us up for today. 8-bit, the 8-bit conversion is not technically an IEEE 754 standard. We do it sometimes in classes, just to make it easier to understand the concept. You know, we only have 8 bits, relatively easy to perform, but it may not be like, probably not going to find it in like most softwares. You will find like the 32, 16, 64-bit, but you're not going to find 8. But anyway, for our purposes, we'll go ahead and go through this 8-bit calculation. One sign bit to represent 1 bit to represent the sign, 3 bits to represent the exponent, and 4 bits to represent the mantissa. So let's go ahead and get the exponent. The exponent for this is going to be super, super simple. I am going to do it this time because why not? So we have 7, that's going to be a remainder of 1, 3, remainder of 1, 1, remainder of 1, 7, it's going to give you 1, 1, 1, right? Cool. We already know that. All right, so that's 111 is going to be our exponent representation. Then we're going to take this fractional portion and go ahead and convert that to binary. This is going to be, again, the same, type of process where we have the times 2 over here. And again, I know I could just run through the slides, but I'm doing this intentionally by hand. So, wow, that drawing really sucked. Okay, I'm doing this by hand so that we can kind of get used to it. Our times 2, we had 0.25. This ends up being a really easy one. 0.5. 0.5, once you bring this over here, that ends up being 1. And we can stop it here. So our number here is 0.01. Super easy for a mantissa, right? Like really, really easy. Boom, got it. We're done. So what's our number? When we get to this portion, it's going to be 111.01. Put them together. Now, the next portion, of course, means we got to move this back. We're only going to move this 2 decimal places. So then our final value, of course, is going to be 1.1101 times 2 to the 2. And that's our representation for that. Now, the next portion of it is, let's go ahead and get our the bias for the unit. All right, so we've just gone through, we did our binary conversions for the whole number. We did our binary conversions for the fractional portion. We combined them. We have our mantissa already, actually. So we got our mantissa. Now we're going to backtrack and kind of get what we need for our exponent. All right, so for our exponent value, we're going to do the precision exponent. The precision is going to be 2 to the, our number of bits for representation is 3. So 3 minus 1 is going to give you 2. 4 minus 1 is going to give you 3. Oh, we have bigger numbers for this. So For this, we have our precision exponent of 3 for an 8-bit number. Now, when we come over here, we want to see what is the bias. We take our precision exponent, we're going to add the fractional exponent to that to get a value of 5. And that will determine what your bias is. And then, of course, we need to convert that to binary. The binary conversion for 5 is going to be relatively simple, 101. And now we have that for our exponent bits. We already calculated the mantissa from before, so this is our 4 bits for the mantissa. We will do, I know I said that one example for that. I'm going to go over one more because I want to see us, I want you guys to see what happens when we're looking at a fractional number for this representation. All right, so let's look at a 16-bit representation for a fraction. The number that we have here is 0.25. Sign bit, that's going to, of course, be 0. 5 bits and 10 bits for our exponent and mantissa. Whole number to binary, there's nothing. So you know what that's going to be? 0, 0, 0. Convert the fraction to binary. We already had this. Very, very simple, right? It's just going to be 0, 1. So what are we left with? 0, 1. That's the entire number. 0, 1. Now, here's where the interesting part comes in. So, because our objective for when we do this kind of exponent and the bias and everything, we want to make sure that 1 is the first number you see in the number. So before, our numbers were all kind of, we had 1s on this side, but right now it's to the right, to the left, and that's because this is a fractional number. So that means that now we are moving this 1, 2 spaces to the right. All right, and as such, our bias, right, for this particular item, that now is going to be -2 because we would have to move it back to the left when we do the conversion backwards, right? When we convert it back to the number. So instead of it being positive, it's now negative. That's also going to impact our ability, our numbers for when we do this exponent bias conversion. Precision exponent, we already know that it's going to be 15. We did that in a previous slide. Now, this is going to be 15 minus 2 because it's a fractional number, which gives us a bias of 13. When we convert 13 to binary, here's the number that we're going to get, 1101. So we can go ahead and insert that into our values there, right? And our mantissa, we already had that before. It's just going to be 0, 1. Or I'm sorry, the mantissa actually is not going to be 0, 1. The mantissa is going to be all zeros because once we move that over, everything else to the right of it were all zeros. So this is our conversion for that fractional exponent. And that was kind of the whole point for doing that, for doing the fractional portion. Now we're going to do just one more quick example, and we'll see what happens if we were to do the same thing with this number with something that perhaps repeats, right? We already know our sign for this is going to be it's absolutely going to be 0, 5 bits and 10 bits. Now, here's what I want us to see. When we're doing this conversion here, we're going to have something that repeats. Or we're going to have something basically that keeps on going. I do not actually want to do all these numbers, so I may stop at some point. So we have 0.24, 0.48, 0.96. All right, I'm gonna just stop here because you guys get the idea of that, and we've done those previously. So let me just stop there. This would kind of be that table that you're looking at. Look at how it's very, very long. And we don't really get any numbers yet that repeat. It's just a very long number, right? We're going to move our decimal point over, right? We moved our decimal point over 2 spaces, similar to what we did before. And this is our number. Now, what I want to show you guys is that this is going to have a different rounding opportunity here. This 10th spot is still our least significant bit, but our post significant bit is 1. So then that means, like I was saying before, because our post significant bit is 1, we have to flip this. So what's going to happen is the actual value of this, I'm going to end up flipping this number. This flips to 0. Now, because that flips to 0, that means I'm going to carry that over here. This then becomes 1. So that's how we get our final value here of the 0, 1, 1, 0. All right, so again, this are our all this is gonna stay the same. 1, 2, 3, 4. All that's gonna stay the same. This is gonna stay the same, right? What happened is I had to flip this number to 0, and then because I split that to 0, you carry over the 1. This became a different number. This ends up getting flipped too. If this was already right, if this wasn't 0 and this was 1, you would keep on flipping the numbers until you get to the end of the decimal point. All right, but anyway, that's how we get to our final value there. Let's calculate our bias precision. It's going to be the same as the other value, 15 minus 2, which is going to give you 13. Convert that to binary. We already did that in the previous slide. It's going to be 0, 1, 1, 1, 0, 1. So that is that. And then here's our mantissa. And that's pretty much it for your fraction. At the end of the slide, you'll see a very useful site that will, if you still have questions for how to do your conversions, I'm going to, in the sources section of this, I do give a very, very good site that will help you kind of go through these calculations, and it'll also show some details and stuff on rounding and all that. All right, that being said, the last thing you want to know is when we're working in C, or we're working with different conversion types, these IEEE standards are going to be standard across these things in terms of how you can do this binary to decimal conversion. And this is a good table you want to look at if you want to think about your mantissa, what are your bias values, your exponents, and your size. All right. All right, and that is it for today. Remember to join and come back online for the next lecture. All right, and enjoy the rest of your day.